Hello everybody and welcome back to ThursDev. I'm Luke and today we're going to start a series of videos discussing what I'm going to call macro game essentials, in which we're going to take a look at the mechanics that drive large-scale games like strategy, builder, and god games, and how we can build a game of that style in Unreal Engine 4. If you're familiar with the engine already, you'll probably understand that the games it handles most adeptly are first and third-person shooters, hybrid RPGs, and games of that sort. Right out of the box, the engine gives you access to all of the standard keyboard and mouse controls necessary to make an FPS, and player character actors are designed to be the avatar of the player moving around in the game map. Ark, the central game we'll be looking at as a platform for modding, is one such game. However, I'd like to step out of Unreal's comfort zone a little bit for this series and see how it handles something it wasn't specifically designed for. The plan is, over the course of the following series of videos, with some interludes from John and Matt, to create a mod in Ark after exploring mechanic design using Unreal 4 as a sandbox that will allow us to build and manage a village within Ark like a god game. If we can accomplish that, we'll go on to see if we can't also automate some of our dinos and iterate onward from there with you, the viewers' input. I'd like to stress as we begin that this video series is going to be documenting the process of creating this mod. A fair bit will be done off camera, and there's no guarantee that we'll even be able to accomplish what we're setting out to do, but I hope that the individual steps will be educational enough to be worth your time. Now, without further ado, building the macro game. To get ourselves started, I'd like to take a look at some top-down camera controls, recapping how to create a free-floating camera actor, and looking at mouse controls and the principles and control schemes to allow us to manage, manipulate, and control numbers of actors in a single game by taking a cursory look at AI actors in Unreal 4 and how we can issue some very basic commands to them. When you start a new project in Unreal 4, there are a number of templates that you can use to get a head start on development. These can be invaluable learning tools and can even be a great groundwork for a project, as long as you want to do exactly what the creator of the templates intended you to do. Among these templates, there's what's called a top-down template available, which gives you control over a character with a camera on a spring arm attached to them to make a sort of top-down, third-person shooter sort of game. Think along the lines of a twin-stick shooter or a top-down space sim. Now, if this is the type of game that you want to make, then you're in good shape and you can start off with the template that they included. But say that you wanted to make an RTS, or a MOBA, maybe a tactical strategy game, or in our case, a god game. I find that it makes more sense typically to start from scratch and build exactly what you want to your own specifications, instead of limiting yourself by adhering to the design someone else already laid out for you. Not only do you get exactly what you want this way, but you also learn how to make it in the process. Particularly when we translate the preliminary work that we're going to do in Unreal 4 over to Ark, we're not going to have access to the templates that UE4 gives us, meaning that we'll have to recreate everything anyway, so why not familiarize ourselves with what we can do right now. When you start any project that requires nudging the engine in a direction it doesn't strictly intend, you're going to have to accept that a certain amount of setup is just an inextricable part of the process. It doesn't have to be painful, especially if you know what you want, but it does require that you understand a few of the basic, essential components of an Unreal Engine game. So the first thing that I'd like to do in preparation of building our God mod is to look at the big three components of any Unreal game: characters, player controllers, and the game mode. All three of these items, like basically everything else in Unreal 4, are presented as individual blueprints, making it fairly easy to create and switch between them. So what are they? Well, some are probably fairly obvious just from the name. A character is pretty much just what you would expect. It's the kind of actor in the game that can either be given an artificial intelligence or function as the player's avatar for purposes of interacting with the game world. Generally speaking, actors are the major dynamic parts of your game. In the case of building a god game, we'll be creating a number of actors, but for now, let's just focus on our first. As with creating basically anything in blueprint-only projects in Unreal 4, the new blueprint is created by right-clicking within the content browser and selecting from a list of available templates. In the case of all three of the classes we'll be looking at today, each is considered a standard blueprint and is readily available when you select the generic blueprint button. We're going to name this actor Player Character Macro Game to denote that this character is going to be used by us as a controlling actor. I should note here that you can really name your blueprints anything that you want, but it definitely behooves you to stick to some naming conventions so that you'll give yourself less of a hard time later on when you have a lot of blueprints to sort through. Epic has favored naming conventions, but as long as they make sense to you and will make sense to anyone trying to help you, name it whatever works in your head. Now, we're not going to make any large changes to our character yet, so let's leave it be for now and move on to the next, being the player controller. As you may once again have guessed, the player controller is a class whose function it is to give the player the ability to issue controls to the character we just created. Most notably, the player character gives us access to the mouse, which we'll need as we go ahead. Let's just enable showing of the mouse cursor, click events, and mouse over events. We may need all of them in the future. Finally, let's go up to the highest level in this particular hierarchy and talk about game mode. What the game mode does, by default, in a nutshell, is to define what classes to use to drive the game, such as which player controller to use, and which pawn or character type to set as a default. Of course, we're going to be setting the two blueprints that we just created in these slots. Once we have these things set up and ready to go, it's simply a matter of implementing them in the game. We need to go to the world settings, which may already be available as a tab next to your details panel, or may need to be opened from your window menu, and set our game mode into the game mode override dropdown. And voila! We've taken our first baby step. Let's see what was accomplished. Not a whole lot at first glance. We've done a few things under the hood, but the only real cosmetic difference now between this and the game default is that we can no longer control our character's point of view with the mouse, and we have a mouse cursor. Enabling the mouse cursor is the thing that we really wanted to get out of this, so mission accomplished. Okay, it's underwhelming, I know. Why don't we go ahead and take the next step, which actually gives us the ability to navigate in our brand new game world. This is where we start to accomplish things that are tangible. Let's pop into our character blueprint and take a quick look at what's inside. We took a look at the character blueprint that we're going to want to create briefly in the last video, so some of you may already know where we're going with this, but let's get ourselves set up. By default, the character class of actor has a capsule component, an arrow component, which basically just tells you which way the model should be facing, a mesh, which is developer speak for the character's model, and a character movement component, which would typically dictate the limitations to our movement. Less so in this case, but I'm getting ahead of myself. What this character will actually do is serve as a camera dolly of sorts. By default, a character collides with its environment, which is something we certainly don't need since we'll be sweeping over trees and cliffsides and the like free as a bird. Let's go to the capsule component, find its collision settings, and set everything to ignore except for world static and world dynamic, which will allow us to travel around the landscape without being blocked by anything except for the landscape itself. Now let's actually set up our camera. As with the last video, we're going to need a spring arm, and attached to the end of it, a camera. It's as simple a matter as clicking the big green Add Component button and typing in what we need, then dragging it to the component hierarchy if we need to attach it as a child of something else. The spring arm is by default attached to the capsule component, no problem, and our camera will connect to the spring arm. Thankfully, when we put them down like this, they're already aligned. In some older versions of UE4, including the ArcDev kit, some manual alignment will become necessary, but it's no biggie right now. Now that the camera's on its boom, let's raise it up to an angle we like. I'm partial to about 70 degrees personally. We'll also want to be sure that it's facing the right direction as compared to the arrow. We'll be adding some yaw and rotation controls down the line, but for now, this will be a fixed camera, so find an angle of view that you like. We should also extend the spring arm a bit so that we get a nice bird's eye view of the landscape. That can be accomplished by finding the arm length variable on the spring arm and changing its value. For reference, assuming the creators of the in-game models were working to standard scale, one Unreal unit is equal to about 1 centimeter. Don't worry, you don't have to start thinking in metric, it's just easier for the engine to operate in a base 100 system. I'm going to set it to 2,500 units, or 25 meters, which is roughly 82 feet if you care about its equivalent in Imperial, which is also a nice high view above the action. With the camera good to go, let's go back to the map view and place the camera and actor into the level. As you can see, we have a collision capsule on the ground and a camera floating high above it, exactly as we wanted. And there we go. Now we have a bird's eye view of our map. Okay, so we have a way to look down on the world, but we still need a way to move ourselves around. That's going to require a little bit more work, so let's close the game window by hitting escape and opening, once again, our character blueprint. This time we want to look at the event graph. Just like the level blueprint, the event graph is where all the real magic happens within Blueprint. Blueprint's what's known as an event-based scripting engine, so that means that everything that's done in the game is called from an executor known as an event or a function. Nothing is just assumed, it always has to be told to happen. So what we're going to do is tell the game what events we want to chain off of, and then what we want to happen when those events do occur. In most top-down games, there are about 3 common methods of moving the camera: via keyboard input, through edge scrolling, and through mouse panning. For today's video, we're going to explore mouse panning because for those of you out there who want to make a mobile game, this is directly translatable to tap and drag to pan. The principle is simple. We want, when we hold down a mouse button, to store where we click the mouse, and while the button is down, to move the actor around like we were moving the world below us. This can be accomplished for a mouse using 2 events: a mouse button event. I'll use the middle mouse, but you can do left or right as you like. Let's define that event now. As you can see, once it's on the blueprint, it has an execution pin for when the button is pressed and one for when it's released. The other event that we're going to need is a little harder to find. We want acceleration, which means the event will execute as the mouse is moved and at the speed that it's moving. The actual application is simple. We want pressing the mouse button to tell the game that the button is down and to set a reference point to move around from. Then when we release it, we want to tell the game that we're no longer trying to move the camera. We want acceleration only to affect the game when the button is pressed, and we want it to move our camera actor around on the X and Y planes, which is side to side and front to back respectively. The Z plane is our up and down, so we don't really need it for our purposes yet. We're going to need 2 variables: a vector, which is basically a set of x, y, z coordinates in the game world, and a boolean, which is basically just a yes or no statement. We'll call our vector clicked location, and our boolean MMB clicked, or middle mouse button is clicked. We're doing this because we might want to track whether the right or left buttons are held down at some point at a later date. So let's start by setting our clicked notifier. From the pressed output, we'll set the MMB clicked variable to true by checking the checkbox. Then from released, we'll set the variable to false. This way, when the mouse is down, it will always be true, and when it's not down, it will be false. Easy peasy. We want to get our vector by checking what's directly underneath our mouse cursor. The mouse is owned by the player controller, so we need to get that. And then from its return pin, we'll create a getHitResult under cursor by channel node. This basically draws a line from the mouse cursor straight into infinity until it hits something, and then records what it hits. For now, we'll leave it as the visibility channel, but we'll be changing that later, but not yet. From there, we're going to be breaking our hit result into a number of possible stats. The important one for us here is the location vector, where it impacted with whatever it hit. As you can see, as you drag a wire from the location vector, it appears yellow. That means it's outputting vector data. We'll use this to set our clicked location variable that we defined before. That will be the next step after setting our MMB clicked boolean. Now, before we do our actual offset action, let's create a few math nodes to get the difference between where we clicked and the current position of the mouse when we're moving it. That will be the basis of our camera movement. From our tapped coordinates variable, we'll drag out a second wire and break the vector into its component floating point numbers, x, y, and z. Similarly, we'll also grab the hit location again. As each time the event is called, it'll constantly recheck that value and break that vector as well, creating 2 sets of x, y, z coordinates. From here, it's a simple matter of subtracting the current x from our stored x and the current y from our stored y using subtraction nodes, and then using those floats to create a new vector by using the makeVector node. We're almost done. Okay, now we need to actually move the actor. From the acceleration event, which has been sitting patiently this whole time, we'll wire out a branch node. A branch is the same as an if-then-else statement. It basically checks a boolean to see whether it's true or false, and then does something based on the result. In this case, we want only to act if our middle mouse button is clicked, so the boolean to check will be our mmBChecked variable. From the true pin, we'll lastly create an addActor local offset node, which will tell the character itself to move relative to its own position to the vector we specify, which is derived from the vector that we just created. Does it work? Let's take a look. I'm going to resize the game window just a little bit so that we can see the whole blueprint in action. While your game is running, blueprints show you visually what they're doing. As you can see, the acceleration is constantly moving. That means that it's checking to see how fast our mouse is moving at all times, but it's not getting past our branch because the middle mouse button isn't clicked. If we click down the mouse button, suddenly the wire lights up and we're in business. Looks pretty good, right? Now there are some other things that can be done to smooth it out and some problems we'll encounter very soon, but so far we're in pretty good shape. Okay, I promise that we're going to have an AI actor doing our bidding by the end of today's video. We won't be doing anything spectacular, but why don't we learn very simply how to tell a character to walk where we want it to. A lot more will go into this as we continue forward, but let's look at the absolute simplest way we can accomplish this. The first thing we're going to need is an actor to move around. I've downloaded the free Anim Starter Pack from the Unreal Marketplace, which gives us a mannequin with some predefined animation, since we don't want to be bothering with doing all of that ourselves right now. Let's create a new character, and then assign him a skeletal mesh and anim blueprint from that pack. I'll get into stuff about these another time. He doesn't need any special bells or whistles, so let's just put one or two of him on the map and leave him there. Now, let's just have them go wherever we click. We'll go back to our camera character and add a left click event. And from here, we'll have to find out who we want to issue orders to. There are some more elegant and less expensive ways of accomplishing this, but let's just get an array of all of the actors of the class that we just defined and issue an order to each and every one of them. That can be accomplished using a getAllActorsOfClass node, which returns an array, or a list, of actors. From there, we'll wire out a forEachLoop node, which means that the next command we issue will be given to each actor in the array. For each array element, we'll issue an AI move_to command, using the same principles as above to get the location we clicked, and we'll get a trace for objects under our mouse cursor, and break the hit result to get a destination vector. Now before the AI can go anywhere, it needs what's called a nav mesh. That's basically a zone that the game tells actors it's possible to navigate around on. We can get a nav mesh bounds volume from our volumes list on the left side of the map panel, and then just drag one onto the map and resize it using the size controls, which you can access by hitting the R key when it's selected. Once it's a reasonable size, we can hit the P key to visualize our nav mesh. All of the green areas are walkable. Let's test it. As you can see, when we click, all of the AI-based template actors run around to the location that we clicked. Not too bad, right? Well, next time we're going to look at how we can select different actors and issue separate orders to them, and also how to have the actors perform actions on their own. Until then, thank you very much, as always, for watching, and take care.